Hey everyone, looking at 11.3 now, dot products. Here's where we kind of start to get interesting. So up until now, we've learned a couple of things. Reminded you of a lot of the things that you probably already knew about vectors. Two dimensions, introduced three dimensions. We talked about adding vectors to get the resultant. We talked about multiplying by a scalar to get parallel vectors. Now we're going to look at one way, because there's more than one way, of multiplying two vectors together. So think back to that last example that we did in 11.2 with the video camera. We basically had to multiply position vectors by a magnitude, a scalar, to get our force. That was an example of force multiplied, or vector multiplied by a scalar. In some problems, you want to be able to multiply two vector quantities together. And there are two ways that you can do that, right? The one that we're looking at today is called a dot product. It also has two other names. It is good to know these names so that when you encounter them later in other courses, you will know what they mean. So dot product is also referred to as scalar product because the result is a scalar, right? And it's also known as the inner product, which interestingly I heard a lot when I was taking quantum mechanics courses. Yeah. So the language varies from discipline to discipline, which is why it's important to know what means what. So the idea with this method is that you multiply together two vectors and you get a scalar. Okay. So there are two different ways that we can find the dot product. One is by using the components of each vector if we know what they are. And this doesn't apply to just two dimensions or just three dimensions. It can be any dimensional vector. And the pattern is the same. It's just product of your first components plus product of your second components plus product of your third components, etc., etc., et merde. And that's an easy way to do it. The other way, which actually is a lot more powerful, is that we can find the dot product by multiplying the magnitude of two vectors times the cosine of the angle that's between them, right? And in two dimensions, well, this would only apply to two dimensions. Three dimensions, it gets a little dicier, and we'll talk about that towards the end of the video. But yeah, with two-dimensional vectors, this is a way for us to relate the magnitudes of those vectors and the angle between them. And the angle sometimes has a lot of significance depending on what kind of question you're answering. So looking at, or yeah, so before I go into examples, recall that cosine of theta always takes on a value between -1 and 1. This means the dot product is always a percentage of the magnitude of u times the magnitude of v. Right? So 100% would be essentially just the product of those two lengths, right? Anything else would end up just being a percentage of it. If you find that u dot v is equal to 0, then we say that u and v are orthogonal. And this is a fancy way of saying perpendicular. What's different about it, though, is that in two dimensions, yeah, these are the same thing. But when you get past that, orthogonal is a more widely applicable term because perpendicular doesn't really tell you a whole lot in three dimensions, right? Because I can be right here, like I can have this vector, I can be in the exact same plane as it. I can be in any plane I want. Any vector along that circle would be perpendicular to vector pencil. Yeah, so orthogonal is the word that we use generally. Right, and remember that means that the angle between them is 90 degrees, and that tracks because what's cosine of 90 degrees? 0. Okay, so we want to draw two vectors and compute P dot Q using both methods. So if I draw the vector 1, 0, I'm starting off at the origin, going over 1 and up 0. So this is going to be vector P. And then vector Q, we go back 1/2. So if 1's here, then 1/2 would be here. And then we're going to go up the square root of 3 over 2, which is a little bit less than 1. And that is vector Q. So now that we've drawn P and Q, we want to find the dot products. So using the simple way that involves the components, we would get that P dot Q is equal to first component times first component. So that's 1 times negative 1/2 plus second component times second component. And we end up getting negative 1/2 as the dot product. And for the second method, we're going to need to do a little thinking here. Because what does the second method require us to have? Magnitudes. Okay, we can find those pretty easily. But we need to know what the angle is between them, which look at these numbers. What do they remind you of? Unit circle. Yep. So if you remember your unit circle, this coordinate, right? So 1, 0 would be at the angle 0 degrees. This coordinate for Q would be at the angle 2 pi over 3. So we know that the angle is 2 pi over 3. Now, if I wanted to find my dot product using that definition, I would need to know the magnitude of P, right? That's the square root of 1 squared plus 0 squared, which is equal to 1. I would need to know the magnitude of Q. All right, and if I square negative 1/2, I get positive 1/4. And if I square square root of 3 over 2, I get 3 over 4. If I add those together, guess what I get? Yep, it's 1, which makes sense since they're on the unit circle. All right, so we've got our magnitudes. We know the angle between the two vectors. So the other definition of dot product, we're going to use 1 times cosine of 2 pi over 3. And cosine of 2 pi over 3 is negative 1/2. So we ended up getting the same thing for both methods, which we should expect. All right, but now let's think about it a little bit. If I were to take a big scary hammer and smush, maybe not a hammer, like a press that you would find in a shop. Don't need that angle distorting things. Anyway, if I were to take some kind of a press and pancake flatten this, Q would end up being this vector here. It has a length of 1/2 and goes the opposite direction of P. In other words, Q, if I were to flatten this, would be equal to negative 1/2 P. Negative 1/2 is the dot product. Interesting. And that's an idea I kind of wanted to plant in your head that we will talk about later in the video. All right. So for the next example, we're just going to be doing some computations. using dot products. So we have these three vectors defined up here. First thing we want is u dot v. Since I know the components of both of these guys, since I know the components of both u and v, I can use that first formula to find my dot product. So first component times first component, that's 2 times 5, plus second component times second component, that's -2 times 8. And we end up getting -6 as our dot product. For B, we want u dot v times vector w. Okay. Notice we're not doing the dot product of this times this. That actually wouldn't make any sense. Because think about it, what are the inputs for a dot product? You have to have two vectors. What is u dot v? That's a scalar. So when I multiply this together, I'm actually multiplying a scalar times vector w. All right. Right, a dot product wouldn't make sense because again, that's a way to multiply two vectors together. This is a scalar times a vector. So we already know what u dot v is. We did that in the last example. So we know that this is essentially just asking us to find -6 w. So I'm going to take each component of w and I'm multiply by -6. And there we go. For the next one, we're taking the dot product of u and the vector 2 times v. So a couple approaches here. Actually, I'm just going to show you the one. Whenever I have to do an operation on a vector before taking a dot product, I find it helpful to write out the component forms for each of these guys. So u has the component form 2, -2, dot, and then 2v is basically just going to double both components of v. So 10, 16. So to find that dot product, we multiply first times first. So 2 times 10. And second times second, -2 times 16. Combining everything together, we get -12. And the last one, the magnitude of w squared. So this is a quantity that does also come up kind of in physics sometimes. In physics, they'll refer to it as norm squared, right? The magnitude squared, which you could get just using the magnitude formula, right? Like if you wanted to use the distance formula to figure out the magnitude of w and then square that, you could, and you should end up getting the same thing as w dot w, right? But this is a definition here. The magnitude squared of a vector is equal to the dot product of that same vector with itself. So to illustrate, I'll show you both. So I know that the dot product, w dot w, we're going to have -4 times -4 plus 3 times 3. There we get 16 plus 9, which gives me 25. So we have w dot w there. Now, I want you to notice something. If I'm taking the dot product of a vector with itself, I'm always going to end up getting this guy times itself plus this guy times itself. When I go to find the magnitude of w, remember that's the square root of first component squared plus second component squared. Notice a pattern there. See, it's component squared plus component squared. So this dot product is basically the magnitude without the square root, hence why it would be squared. So we end up with the magnitude being the square root of 25, which is also known as 5. And squaring the magnitude would give me 25. So we arrive at the same answer. All right, next example. For these vectors, u, v, and w, find the angle between u and v, then find the angle between u and w. So for u and v, first thing we want to do is figure out the dot product. Because remember, the dot product can be related to the angle. Right, so the dot product, we have 3 times -4. We have -1 times 0. And we have 2 times 2. So the dot product is -8. Remember, the dot product is also defined as the magnitude of u times the magnitude of v times cosine of the angle between u and v. So we need to figure out the magnitudes for each of these. So the magnitude of u, right, 3 squared, 9, 10, 14. So the square root of 14. The magnitude of v, 16, 0, and 4. So that's the square root of 20, which can be simplified, but won't worry about that. And the magnitude of w, we have 1 plus 1 is 2 plus 4 gives me the square root of 6. Okay, so for u and v, I only need these two numbers, square root of 14 times the square root of 20. All right, and 14 times 2 is 28. Put a 0 at the end, you got 280. So that's the magnitude of u times the magnitude of v. And we're multiplying that by cosine of theta, where theta is the number between, or the angle between vector u and vector v. This is where it would actually be very prudent for us to simplify the square root, because when we're solving trig equations, one thing that's kind of important is to be able to recognize unit circle numbers when we see them. And if I don't simplify this, I won't be able to recognize unit circle values even if there is one. So let's try and simplify that one real quick. So I mentioned earlier that this guy could be simplified. Square root of 20 is the same thing as 2 square root of 5. 14 is 7 times 2. Right? So I can't really take anything out of that square root. But that means that I could simplify the square root of 280 to 2 times the square root of 14 times 5. So we could write this as 2 square root of 70. In all honesty, though, that's not going to help us because this is not a 3 or a 2. Right? If we can make it so that we leave just the square root of 3 or just the square root of 2, then there's a good chance that we'll end up getting a unit circle value here. Here we won't. So we actually have to rely a little bit on some technology to figure out what cosine of that that angle is. Right, in the meantime, let's just focus on solving this. So we know that cosine of theta, right, we have to isolate the cosine first. It's going to be equal to -8 divided by 2 square root 70. Simplifying that, I would get -4 over the square root of 70. So the angle theta would be arc cosine of -4 over square root of 70. right? And again, we could use a calculator to find the inverse cosine of that angle. For U and W, switching gears now. All right, same approach. We want to start by finding the dot product. So U dot W, we get 3 times 1, 3, -1 times -1, and 2 times -2. So when I add those together, I end up getting 0. 0. Remember, what does that mean? That means that U and W are orthogonal. Yep, meaning that the angle between them yep, meaning that the angle between them is 90 degrees, or the sophisticated answer, pi over 2 radians. And there we go. So next we're given a couple of things. We know the magnitude of U, the magnitude of V. We know the angle between U and V. We want to find the dot product. So based on the information we're given here, we can't actually use the component formula for dot product. Instead, we just have to remember the other one, where we multiply magnitude of U, magnitude of V, and cosine of pi over 4. So this is going to give me 70 multiplied by the square root of 2 over 2. Remember, the over 2 we can interpret as dividing that coefficient by 2. So we get 35 squared of 2. All right, now to get into something, yeah, now to get into something a little more yeesh. So remember earlier I mentioned that the dot product formula that tells us the angle between two vectors is mostly useful in 2 dimensions. Well, that's because in 3 dimensions, what angle would we even be talking about, right? There are a lot of angles that we can discuss when we move into 3 dimensions, especially with 3-dimensional vectors. Like it can get really wonky, especially if we're talking about vectors in standard form where the initial point is at the origin. For 3-dimensional vectors, yeah, well, actually for 2-dimensional vectors, remember we could talk about the direction of a vector by looking at the angle between the vector and the positive x-axis. There's not really an equivalent for that in 3 dimensions, so we have to calculate what are called direction angles or direction cosines, right? And the way that we figure these out is by using that dot product formula with the angle on the vector in question and each of the unit vectors, I, j, and k. So looking at this example, we've got a vector v, we know the components of v, and we want to find the direction cosines and direction angles. So starting off, we're going to start with v dot I. So v dot I, if I use my component form, is going to be, let's see, 2, 3, 4 dot 1, 0, 0. If I look at the dot product for that, I get 2. In fact, if I take the dot product in this way with each of the different unit vectors, I'm going to end up just getting that component for the dot product. So we know the dot product v dot I is 2. We know that this is also equal to the magnitude of v times the magnitude of I times cosine of the angle between them. So magnitude of v, we're going to need for this one, we have the square root of 2 squared plus 3 squared plus 4 squared. So that's going to give me the square root of 29. Okay. So we have the square root of 29 multiplied by 1, right? Because remember, I is a unit vector, therefore its magnitude is 1, times cosine of the angle between v and I, which we are going to refer to as alpha. All right, so alpha is the angle with the x-axis, beta is the angle with the y-axis, and gamma is the angle with the z-axis. So solving my trig equation here, we end up with cosine of alpha is equal to 2 over the square root of 29. 29 is a prime number. I cannot simplify that radical. So we know that, living life on the edge. So we know that we would need a calculator to get an exact number, but we could also refer to this as alpha equals arc cosine of 2 over square root 29. All right, and that's going to be the direction angle for x-axis. Now, if I do the same thing with the y-axis, v dot j, I know that the dot product is going to end up being equal to the y component. And then I know the magnitude for v is square root 29. Magnitude for j, a unit vector, is 1. And cosine of beta. So beta, again, is the angle between the vector on the y-axis. Okay. So again, solving my equation, I get cosine of beta equal to 3 over square root 29, which means that angle beta is going to be equal to arc cosine, which we can also write as cosine inverse, of 3 over square root 29. And that's angle beta. Now for gamma, we're going to look at v dot k. We know that's going to result in the z component of the vector, 4. And we know that we're going to end up getting a very similar equation. All right. So we know that cosine of gamma, not 2, cosine of gamma is 4 over square root 29, which means that angle gamma is equal to arc cosine or cosine inverse of 4 over square root 29. And at this point, we've found all of our direction angles. The direction cosines are 2 over root 29, 3 over root 29, and 4 over root 29. Now, the last part of this question asks us to show that cosine squared alpha plus cosine squared beta plus cosine squared gamma is equal to 1. So to do that, we know that cosine of alpha is 2 over square root 29. If I square that, that gives me the first term. We know that cosine of beta is 3 over square root 29. Notice I'm talking about cosine of the angle, not the angle itself. right? That's why I'm not using arc cosine. And then cosine of gamma, we know is 4 over square root 29, right? And then if I square everything, first term we get 2 squared is 4 over 29. Second term, 3 squared is 9 over 29. Third term, 4 squared is 16 over 29. If I add these together, 4 and 16 make 20, plus 9 gives me 29 over 29. And guess what? That's 1. So we know that that statement is true.